Chapter 4, Probability. Section 4.2, we're going to talk about the basics of probability. Start off with some definitions. We call an event any collection of results or outcomes of a procedure. A simple event is an outcome or event that cannot be broken down into simpler events. So, for example, an event might be rolling a pair of dice and getting a sum of 7. There are several ways for this to happen. You could get a 1 on the first die and a 6 on the second die, or maybe you get a 4 on the first die and a 3 on the second die. So this is an event, but we could break it down into simpler events there. So it's not a simple event. But a simple event might be rolling a pair of dice and getting a 5 on the first and a 2 on the second. So this cannot be broken down any further. So just to illustrate that, an event, we have several ways of the event occurring. Whereas a simple event, there's only one way for it to occur. The sample space for a procedure consists of all possible simple events. So for example, consider rolling a pair of dice. Now the sample space would include getting a 1 on the first die and a 1 on the second die, but it would also include getting a 5 on the first die and say a 6 on the second die. So it includes all these different possible combinations. If we list them out in a table, we have something that looks like this, where the first number represents the first die and the second number represents the second die. Notice there are 36 different possible simple events in this sample space. Another example, consider 3 births and let an event be getting 2 girls and 1 boy out of those 3 births. There are 3 different ways that this can happen. Either a girl, and then a boy, a boy, and then a girl, a boy, and a girl, and then a girl. Each of those individually are the simple events. Together they make up the event as a whole. The sample space would of course include those 3 simple events, but all the other possible simple events that don't include getting 2 girls and a boy. So the sample space would also include the simple event of getting 3 girls, a girl and 2 boys, or 3 boys. A couple notational issues. We use capital P to denote the probability, and this will be a number. We use A, B, and C to denote events. So these aren't numbers, but they're events, such as rolling a sum of 7 on a pair of dice, or getting 2 girls and a boy out of 3 births. Putting them together, P of A, or P of B, or P of C would denote the probability that that event A, B, or C occurs. As an example of how we use this notation, we might say, let A be the event of rolling a 3 on a pair of dice. Find the probability that A occurs. We have a few approaches to probability. The first we'll talk about is the classical approach. One thing to keep in mind as we talk about this is, in order to use the classical approach to probability, every simple event needs to be equally likely to occur. So what we do with the classical approach, in order to find the probability that an event A has occurred, we first find the number of ways that A can occur. That is, the number of simple events that make up A. Then we think about how many simple events are in the sample space, and we divide by that number. As an example, let A be the event of rolling at least 1 3 on a pair of dice. Find the probability that A occurs. So using our formula, we want to find the probability that A occurs. So let's consider the sample space. Now if we think about the simple events that have a 3 occurring on the second dice, that's going to be the 3rd column over. So it'll be all these rolls with a 3 on the second dice. Also, we want to consider what happens when we roll a 3 on the first dice. So that's going to be this third row down. So these are all the different ways that we could get a 3 on a roll of 2 dice. So the probability that A has occurred, to find that, we want to count up the number of ways that we can roll a 3 on at least one dice. So we circled 11 different possible simple events, and we know that there are 36 different simple events in our sample space. So we simply divide those and come up with either 11 over 36 or 0.3056 as the probability that we would roll at least one 3 on a pair of dice. Again, let me emphasize, we want to make sure when we're dealing with the classical approach to probability that each simple event is equally likely to occur. The second approach is what we call the relative frequency approach. This requires us to collect some data first and find out how often a certain event has occurred. So to find the probability that an event A occurs, we first count up the number of times that event occurred and then divide by the number of observations, or the times the procedure was repeated. As an example, suppose we wanted to find out the probability that there will be an accident on a particular freeway curve. Well, what we first need to do is count up the number of accidents we see on a freeway curve and divide that by the number of cars that drove by. This would give us an approximation of the probability that there will be an accident on that freeway curve. This leads to a discussion about the law of large numbers. As a procedure is repeated over and over, the relative frequency probability of an event tends to approach the actual probability. So for example, on the freeway accident problem, if we observe one car driving by and we see that it did not get in an accident, we wouldn't say that there's a 0 probability that there will be an accident on that freeway curve. We would repeat the procedure over and over again, and the more we repeated it, the closer our approximation would be to the actual probability of getting in an accident. Another example, we know that rolling one die, there's a 1/6 probability of a 1 coming up. So let's say we wanted to use the relative frequency approach to verify that. So you roll a die and you get a 2 coming up. Now that means 0 out of 1 roll we saw a 1. But of course it's not a 0 probability that a 1 will come up, because if we roll again we might get a 1. So now 1 out of 2 rolls we've seen a 1 come up. However, we still wouldn't say there's a 50% probability that a 1 would come up. We'd continue to roll the die, count how many times a 1 comes up, and then divide that by how many times we rolled the die total. The more times we roll the die, the closer this probability should be to 1/6. Complementary events. A complementary event consists of all outcomes in which A does not occur. We denote it with this A overline, or what I'll call A bar. So as an example, if we roll a pair of dice, and A is the event that we roll a 5, determine A bar. In other words, determine the event that we don't roll a 5 on a pair of dice. So again, consider the sample space, and I've circled all the simple events where we roll at least one 5. So A bar will be all the simple events where we don't roll a 5. That is, anything that's not circled. Or, here, anything that's circled in red. This is A bar, the collection of these simple events. Another example. Given the sample data in the following table, first let's answer the question, how many responses were actually lies? What we're looking at is polygraph results where we got a positive test result for some people who did not actually lie and some people who actually lied. And we got a negative result for some people who did not actually lie and a negative result for some people who actually did lie. To answer question 1, how many responses were actually lies, we just simply need to count up 42 plus 9, the people who actually lied. So that'll give us 51. Question 2 says, if one of the responses is randomly selected, what is the probability that it is a lie? So we can use the classical approach to answer this question. First, we want to count up the number of people who actually lied, then the number of people who were surveyed for these results, and divide the two numbers. In other words, we're going to take 51 and divide by the total number of survey respondents, 98, and we'll get a probability of about 0.5204. A third approach to probability, let's consider this example. What is the probability that you will get stuck in an elevator? Now, if we don't have past data on elevators getting stuck, we can't use the relative frequency approach. So then we might think, can we use the classical approach? Well, if we try the classical approach, we have to consider that there are only two possible outcomes. You either get stuck in an elevator or you do not. However, the probabilities that those two simple events the probability of those two simple events are not equally likely. So we can't use the classical approach. If they were equally likely, then there's just a 50-50 chance that you're going to get stuck the next time you take an elevator. And of course, that's not the case. So we have to use the subjective probability, which is basically a rough estimate and using our intuition. So if we know that it's very unlikely that we're going to get stuck in an elevator, we would say that the probability is very small. And we might put a number on it like 0.0001 or even smaller, 0.00001. An unlikely event is an event with a probability that is very small, such as less than 0.05. Not to be confused with an unusual event. An unusual event is one with an unusually high number of outcomes or an unusually low number of outcomes. And we call this an extreme result. So as an example of something that's unlikely but not unusual, consider this example. The probability of flipping a coin 1,000 times and getting exactly 500 heads is approximately 0.0252. This is an unlikely event, even though we expect to get around 500 heads. So since we expect to get somewhere around 500 heads, we wouldn't call this unusual, because 500 is not an unusually high or unusually low number of heads. But the probability of getting that exact number is unlikely. As an example of an unusual event, suppose we flip a coin 1,000 times and get exactly 5 heads. This is an unusual event because we're expecting a number closer to 500. Since this is so small, we call it unusual. Similarly, if we got 995 heads, we would also call that unusual because 995 is such a high number from what we expected. The rare event rule is a rule that will come up several times throughout the semester. For now, we'll just introduce it with an example. Suppose we are given a coin, and we're going to assume it's fair, meaning each side has an equal chance of coming up. So there's a 50-50 chance that we'll get a head or a tails. Alright, suppose we flip that coin 1,000 times and we get exactly 5 heads. The probability of getting so few heads with a fair coin is so small, we have to change our original assumption. So now we have to assume that it's not fair, because it was so improbable that we would get 5 heads or fewer, that we must assume that this is not fair. A few important principles to keep in mind while we're talking about probabilities over the next chapter. First of all, the probability of an event is a fraction or decimal between 0 and 1, always. Although we can include 0 and 1. So for the probability of an impossible event, we use 0. For the probability of an event that is certain to occur, we use 1. all other probabilities fall between those. If A is an event, then the probability of A bar denotes the probability that A did not occur. And lastly, the probability that A did not occur is simply 1 minus the probability that A occurred.